I want to welcome everybody to another erode class. Very pleased to be rejoined by our friend Mike Kaplan. And this is on the website. Today, Mike's going to talk about what causes the Andes to rise up and erode down. Just as a reminder, the Andes are along the west coast of South America. But more importantly, here is Belo Horizonte with some of the best food.
The website. Wasn't the website coming from Brazil?
No, we do things with people in Belo Horizonte, and just north of Belo Horizonte is Chiamanchina. So I have some resources if you'd like to follow up on some of the things that we'll hear about today. And here's a link to two of Mike's previous talks. So at this point, I'm going to turn things over to Mike.
Well, thanks. Glad to be back. I think actually it's the fourth time. I did something on the Little Ice Age as well. And that's all about how glaciers change and how most of those focused on looking at how glaciers changed in the past and trying to use that to understand how the climate has changed in the past, because before instrumental records, there's not too many ways we can learn how the climate has changed in the past. Like, how has it swung naturally before humans may have had an impact? So those were the three prior E2C workshops I was part of. This one's quite different, and it's based on a project we've had now for a few years, supported by the National Science Foundation, which is ultimately supported by taxpayer dollars. So I thank all of you, viewers like you. And this project is a little different. I actually wrote the grant right 4 years ago exactly, right now in April. Remember, everything was shutting down. And that's when I wrote this grant proposal. It's like one of the first things I did stuck at home. I was so busy because we were trying to switch a bunch of stuff to online, including our summer intern program. But I also wrote this grant proposal, submitted it, and got it funded during COVID. So this project is a little different than the others. It's also focused on looking at glaciers, more in the central Andes. The other thing is the previous E2C workshops were more focused on Patagonia, which is the southernmost part of South America. Today I'll be talking a lot about Patagonia, but the project that kind of motivated me or inspired me, if you will, in terms of this workshop today is a project in the central Andes. And this project is we're more interested in how the mountains have changed over time, how they've eroded down, specifically the effect of glaciers. So how glaciers erode mountains. And that's the focus of one of the projects I have now. And I'm leaving for Argentina in the field area, less than 3 weeks now. It's Friday night. So yesterday, last night, in 3 weeks, I'll be heading. So I'll be waking up about now in Santiago 3 weeks from now. And the project, we're interested in one, how mountains erode, like the effects of rivers, glaciers. I'll talk a lot more about that today. And just in general, how the mountains may evolve due to geomorphic processes. But I'm going to talk a lot about Patagonia because the effects of glaciers on how mountains change is really strong when you look at the Patagonian Andes. And actually, the slide on the left, this is the Matterhorn, for those who've seen the Matterhorn. And those two little things at the top on the sides of the Matterhorn are the hacksaw and the buzzsaw, because I'm going to introduce something today if you haven't heard of the buzzsaw idea. And the buzzsaw idea is that glaciers, because they erode the mountains, they cause these shapes like the Matterhorn. They're like a buzzsaw to the mountains, and they limit how high the mountains can get. And it's one of the things that we're this process or this idea that's been in the literature for a while, the buzzsaw hypothesis. It's one of the things we're really interested in this project, how the Andes evolve in part due to this buzzsaw idea that glaciers, because they erode, they might limit the height of mountains, or just in general, really play a key role in how mountains change. So I'll talk more about that today as well. And the slide on the right is Patagonia, and it's one of the, we say, one of the key areas that people, when people discuss the buzzsaw, the Andes in South America in Patagonia are one of the key sites. And I'll talk more about this also. But you could see, you know, there's limits to the height. Nothing in Patagonia, you think of the Andes as being very high, and it has some of the highest mountains, certainly outside the Himalaya. But actually in Patagonia, well, it's all relative, but nothing goes higher than about 14,000 feet. And most of the mountains are actually much lower. And so one idea is because they've been chewed up by glaciers over the last million years. So here's another title of the talk could be, and one of the themes of today is how, is thinking about how mountains grow, how they erode down. And as I'll mention, over the last few decades, there's been a lot of new understanding about how, sorry, I need some water. That breakfast was a little bit too much, maybe. Heartburn. Another alternate title of today could be how different things affect how mountains develop and change and evolve over time. The possible roles of glaciers, climate, tectonics. Obviously, tectonics is needed, right? You're not going to have a mountain get high without plate tectonics and mountain building. And how this causes the evolution of the Andes. So this could be another title. Another title could simply be, you know, well, similar to what I wrote, how what goes up either stays up or erodes down, you know, something like that. But these different, that one of the themes of today is that how mountains develop over time, if they're still active, is really an interplay, or many things play a role. Right? We think of mountains, well, I don't know. Before I was a geologist, I thought of mountains as they shoot up in the sky. You know, and clearly they erode down, but I didn't think, well, we have all these many things that affect each other. We have tectonics, right? That's the ultimate thing that causes the mountains to go up. This included the Appalachians around here when Pangea formed. In climate, what the climate is and how that affects how mountains change plays a key role. And now, towards the end of the talk, I'll actually introduce a study people have been testing that may say, well, actually, people thought maybe tectonics came first and then the climate modified how the mountains grew. But now there are studies or hypotheses that maybe climate itself helps the mountains grow. And I'll talk about that a little bit also. And then erosion, of course, and this is what my main interest in, is how the mountains may erode down. And there's a couple key things I'll mention today. Precipitation. Once you get mountains built up high, you start to get things like the orographic effect, a lot of rain, a lot of rivers, they carve out mountains. And then glaciations, right, which is the one my research, what I tend to be obsessed with most days. And then there are all these other things. So this is from a paper by somebody named Sean Willett. And it was based on a conference already almost 20 years ago, where there were three of them that led the conference. So we really need to think about all these things when we think about how mountains evolve. It's not just a simple mountains go up, they erode down, etc. How do these things interplay? What are their different roles? How do they feed back on each other in terms of mountain development? So first I'm going to talk about, you know, the Andes rise up. Now I'm not going to spend much time on what causes the Andes to rise up. And the main reason, it's not my expertise. You know, I'm always, I sort of can read the literature, I have an idea, but most of today's workshop is more on how they erode down and actually whether erosion itself can help them rise back up. And I'll give I'll talk about that as I mentioned. So this is actually kind of brief because one, it's not really my expertise. And I don't do research so much on, what causes the Andes to rise up, but from basic, we think it's rock uplift, rock being uplifted due to plate tectonics, right? The west side of the South American plate. So here's the South American plate. The Nazca plate and the Antarctic plates are being subducted under the South American plate. So it's one of the world's classic subduction zones. That's why there are earthquakes. It causes compression on the west side of South America. And just similar to when continents collide, mountains go up, whether it's the Appalachians 500 to 200 million years ago, or it's the Andes now, or the Himalayas. This is a classic example of an oceanic crust being subducted under continental crust, just like Alaska or the west coast of the parts of the west coast of the US, or places like Washington, Oregon. And so you have mountains fringing the west side, in this case, the west side of the continent. So where are mountains today, right? You think the big mountains that are forming today, the Himalaya, right? The Himalaya are due to the India, that plate crashing into the Asian plate. That's an example of just two continents crashing into each other, mountains going up. The Sierra Nevada, also probably partly due to this kind of thing where the Pacific plate is being subducted down under the North American plate, or else like Japan. That's similar to this. It's part of an oceanic plate being subducted under Asia. So this is it.
Alps.
The Alps are in Europe are due to ultimately due to the African plate crashing into the European plate. Right? So, and folks at home may be able to see this. So can everyone see this if I stand like this? So this shows, just cover this screen. If folks at home could see part of this, it's just a map of the different plates. I assume, most folks have seen different variations of this. The Murray thought figures are another way. And they show, the ring of fire, right? Around the Pacific, places where mountains are going up because continents are colliding, mid-ocean rifts. So here's South America. And it's again that the Nazca and the Antarctic plates being subducted under the South American plate. And there was a rift here, a mid-ocean rift. Pieces of that rift have also been subducted under South America, and that's caused a lot of present heat and volcanism there. So here's, the Alps. The Alps are not too, but it's basically Africa and Europe colliding. Alaska is the Pacific plate being subducted under these high latitude plates. All the New Zealand. Some of these are ocean plate collisions. And so you get places like New Zealand and a lot of the Southwest Pacific Islands, which are all volcanic, etc. Thanks, Mike. So, and the Andes, they're one of the youngest, they are truly one of the youngest mountain ranges. And I forget the numbers, but let me go back. But they're really a young mountain range, right? Much has happened in the last 10 or 20 million years. Maybe 30 million years. Maybe things started 50 million years ago, but they're really the Cenozoic, especially the last, let's say 20 million or 30 million years. And I think much of the uplift has happened probably even more recently, but it depends where you look exactly and which part of South America, but the Himalaya are also a very young mountain range, but off the top of my head, I'm guessing the Himalaya and the Andes are the two youngest mountain ranges we have, right? And the Alps are, I don't know how much they're actually going up still, but they're still active probably. But the Andes are one of the youngest. and much of the volcanism, and again, this is outside my expertise, but when I hear about uplift rates and volcanoes and things forming, I see numbers of since the Miocene or since 20 million years ago. Quite young. This is a more detailed on the left, my left, your left, of the subduction zone, the Antarctic plate, the Nazca plate. I mentioned a few minutes ago pieces of, it's called the Chilean rise. It's basically like a mid-ocean rift, like the mid-Atlantic rift. They have actually been subducted under South America, and this has caused a lot of the volcanism and perhaps uplift. So this is zooming in a little bit on the plate tectonics. This figure we put together for a paper, and it's more concerned with where the glaciers and the ice sheets were. These outlines you could see, so this thick black line, these dashed lines, those are limits of what's called the Patagonian ice sheet. So Patagonia, or the Southern Andes, did have a narrow, small ice sheet, just like the Laurentide ice sheet over Lamont Doherty. The Laurentide ice sheet, which covered Lamont Doherty, was the biggest ice sheet on the planet during the Ice Age. I guess it was even bigger than the East Antarctic ice sheet. Maybe it was about the same order of magnitude as the East Antarctic ice sheet is today. But these outlines show the extent of the Patagonian ice sheet. And they're covering the Andes, which are on the west side of the continent because that's where the plates are colliding. And you can see most of Western South America was covered by the ice sheet. And this caused a lot of glacier erosion. I had this figure which also showed pieces of the rift, but it's kind of hard to see. Maybe the folks on Zoom can see it. But this Google Earth image on the right, the blobs in white are the present ice fields. So that's the largest two glaciers in Patagonia, the South and North Patagonian ice field. And today they're quite small, but they're probably still causing a lot of erosion. But the ice sheet during the Ice Ages covered all the Southern Andes. Oh, yeah, so here's that image I just showed, the Nazca plate, Antarctic plate. There's a Scotia plate a little bit in the south, but I don't think that's doing much for plate tectonics and the rise of the Andes. I guess there used to be a small anticlinal plate. And then most of my discussion is from the central Andes south. I don't know nearly as much about the very northern bit. So here's this figure. So that's about as much I'm going to say on the tectonics bit and the rise of the Andes. And it's, again, it's for me to learn, I also had to kind of go to the literature. And I think, things like Wikipedia, I would never recommend Wikipedia for basic research, but to summarize definitions, time periods, basic stuff, I go straight to Wikipedia. If I want to know, basically when the Andes rose, I'll look it up on Wiki. I've never used it for basic research, but just to look things up as an encyclopedia, it'd be like going to the Encyclopedia Britannica when I was a kid. And so that's the tectonics bit. The rise of the Andes is, given some expertise, I could really simplify it. Probably the people who study this will say, oh, it's not that simple, but to me, it's like, well, the plates collide, the Andes go up. And I know it's more complicated than that, but that's the rise. The rest of the lecture or workshop will be focused on how they then erode down.
Approximately how high per year, per century are the Andes rising?
That I don't know.
Okay, because I know I've.
That's a question I'd have to look at.
Extensive trips, and we've heard about the Alps and what having, they tell us how much they're going up, and just curious.
I don't know that number. I think some parts are probably not rising right now.
Okay.
Like I think also Patagonia in the southern part, they're not rising as fast as they were 5 or 10 million years ago. In fact, they may not be rising much because now, as I'll start to discuss, one idea with this buzzsaw is it creates this kind of equilibrium where how much they rise gets cut down by glaciers. So it's kind of in balance. The central Andes, they're not covered as much by glaciers. It's too warm, it's too dry. So those areas could still be rising. But no, that's a number I'd have to look up, for example, yeah. What are the Alps? Do you know any numbers off the top of your head? Or?
Well, we were in Zermatt, we were at the Matterhorn, they were telling us 1 to 2 inches a century.
Yeah, I mean, it might not be in a big picture, it might not be that, if you really generalize, maybe two different, just so fast, maybe things can rise, but I also think of the Alps not rising as fast as maybe they were 20, 30, 40 million years ago. But yeah, I think it probably depends where you are. Some areas may be in balance, more or less. And then other areas are still rising, yeah. So the rest of the talk will be more on the bottom part of this figure, where we're looking at once the mountains start to go up, how do they erode down? Perhaps how that balance I just mentioned, going up and coming down, they stay in balance. Perhaps climate erosion, actually, I'll touch upon this. I mentioned it already. They actually may play an additional role in helping mountains go up. And I'll mention that in some areas. So I think what causes, to step back, what causes mountains to erode? And I'll kind of give you answers. And there are many things you could say, you could make a long list. But to me, there are the two most important things that cause mountains to erode. Not so much the Appalachian anymore, although it could apply maybe to the Adirondacks or Vermont or New Hampshire, and that's rivers and glaciers. They both, due to gravity, once you get the mountains high enough, it's going to rain and they're going to erode. And rivers and glaciers, they're both, in terms of flow, they're just going to flow towards the lowest elevation. So once you have mountains, once you have land rising, well, first you're going to get rivers, right? Because it's going to rain, the rain has to go back into the sea. So this was an interesting article which summarized, the two things. For me, rivers, which can cause these narrow valleys, and glaciers. This is Yosemite. And rivers, we tend to think of rivers more, the signature on the landscape of river erosion or fluvial erosion is the V. This image has both, it's nice, I think it's from this paper, if I remember, where it's showing both what river erosion looks like and glacier erosion. The river erosion is more narrow valleys. You think of these steep gorges in the Himalayas. They cause more of, we say, the V shape. Glaciers tend to, we think, if they're eroding over time, cause more of the U shape. And that has to do with how glaciers will erode out their beds and their sides. And I could give a whole talk just on that. But if we simplify things, I think you could say glaciers cause things like Yosemite. This I think is in the Sierra Nevada, this photo. And rivers tend to be the V or more narrow. Thanks, right? These are the two, to me, the two biggest. Now there's all kinds of other stuff. You have landslides, rockfall, but to me, the focus, the two biggest things are how the river networks, maybe not just the rivers themselves, but the whole network, how they eroding down a mountain, and then how glaciers erode. And it's still a current focus of a lot of people, including myself, as I'll mention, is how fast these different things, the relative importance of one or the other. Do glaciers erode much more than rivers? Do rivers erode much more than glaciers? A lot of people are focused on this in the Himalayas, in the Andes. And that's one of the things that led me to write that grant proposal, which we've been focused on now, which ultimately led me to say, oh, I'll give this talk on how mountains erode down and rise up. So climate and erosion, as you remember from that flow chart with arrows going every which way, the climate can really influence how mountains erode for many reasons, but two reasons, to think of it as two generalizations. One is rain, as I mentioned, right? Once you get the mountains rising, you start to get things like an orographic effect, like the Sierra Nevada, not so much the Alps, the Andes, Sierra Nevada, where the west side's really wet, New Zealand, and the east side's more dry, classic orographic effect. So you think the west side is just lots of rain, the rain has to run off, that causes rivers erode, mountains erode. The other thing, once the mountains get high enough, they're gonna get cold enough for glaciers to exist. And for a glacier to exist, you have to have year after year of snow building up. There's always going to be some snow that doesn't melt in the summer. Right? It's cold enough in the summer that you might have melting some of the day or part of the day, but it's not cold enough that you don't get rid of all your snow each year. And that when that happens at decade after decade after decade, the snow builds up. The pressure of the snow at the bottom of the snowpack turns into ice. The ice builds up. This happens after a few decades and you get a glacier. For all that to happen, the mountains have to reach a critical height. It has to be above what we think is like the 0 degree isotherm in the atmosphere, 0 degree Celsius, because that's 32 Fahrenheit. Once you get below 32 Fahrenheit, things get frozen. It snows, it doesn't rain. So that for a glacier to grow, the snow has to survive the summer heat. And so the way to survive the summer heat is your mountains get high enough that it's cold because you're up high. So eventually the mountains will get high enough where your glaciers grow. And so the second way climate really impacts erosion is because when it gets cold enough, it snows. And when it snows, you get glaciers. And eventually they become big enough that here in Patagonia, during an ice age, you get even an ice sheet. And the ice sheet causes a lot of erosion. In the Alps also, mountain glaciers, they erode them. So now the glaciers in the Alps, they're now retreating. They're getting smaller because climate's warming. If it wasn't warming, then these glaciers have been there because the summers have not gotten warm enough to melt them completely away. They are now, but at least until, let's say, a few decades ago, they weren't. So this is our buzzsaw, which I'll discuss a little bit more. And the idea of the buzzsaw is that glaciers are so good at eroding the landscape that they're on that they really limit how high the mountains can get. Now, one of the things that glaciers, some of us say they do is they eat away at the area. Glaciers erode the area in which they're growing in. We call it some of us call it like a self-defeating mechanism. They're kind of killing themselves, so to speak, right? Because they're eroding the high peaks. You think of the Matterhorn, so narrow now because the glaciers have been eroding the sides. And oops. So this is I'll go back to the video, but this is pictures you could think this is the glacier. One of there's two places a glacier does a lot of eroding. One is at the top of the glacier, like a small glacier. So here's something that might look like in the Alps. In parts of Patagonia that have small glaciers, and a lot of erosion happens right at the top. So this might be the Matterhorn 200 years ago, 300 years ago during the Little Ice Age. And the reason it happens at the top is you get melting in the summer. That water percolates down, and then it freezes at night or it freezes during the winter. As you know, ice has got more volume than water, so it expands. And so that causes a lot of breakup of rock at the high areas at the tops of the small glaciers, like in the Alps around the Matterhorn. This is a really effective erosion process. The other place you get a lot of erosion is along the base, in particular, where the ice is thickest and it could be sliding the fastest. So glaciers can slide on their beds if the bottom is at what we call the pressure melting point or at the freezing point, if there's a thin film of water. And that causes a lot of erosion. So glaciers can erode along the sides, at the top, especially when they're small, and they also erode along the bottom. And this includes an ice sheet. Like when this area is covered by an ice sheet, there are no hills sticking through the ice sheet, at least during the peak of the ice age. So it's only eroding at the bed. Now, let's see if this video, this might be asking for trouble, but let me see if I can. When I did this last night, it gave me all these kind of commercials, which seem totally inappropriate, but there's no volume, so it's just a video. So here's the mountain growing. I thought accidentally we'd go to one of my Allman Brothers videos that I've said, but So up until then, it's just fluvial erosion or rivers eroding. And then this is like the 0-degree isotherm. We call it the snow line altitude. So now the mountains have poked through the snow line altitude of the 0-degree, 32 Fahrenheit. And now you're going to get glacier erosion, right? So if we go back, mountains are growing. Growing. We're getting rivers, fluvial or river erosion. We go high enough in the atmosphere that we're through the freezing point, in the summer especially, and then we start to get glaciers eroding. And glaciers, you could think of this as like a schematic of the Matterhorn. And the glaciers start to erode the high areas. And this top dash line, in a cartoon type way, could be like the glacial buzzsaw, because the mountains get high enough due to rock uplift. Glaciers start to form, they start to erode. They're kind of eroding where they grow in this self-defeating mechanism. Ooh, who's that?
That's the next one.
No, I know, I'm joking. Now I have to get rid of this thing.
Sorry.
Yeah.
Is that video like your own personal video or is that?
It's on the website.
No, I did a Google search.
Okay,
Yeah, no,
that's it. No, but that's a great video.
It's
Yeah.
available on the website.
Okay.
yeah, Mike put it on the website. No, I just did a Google search because and there's several of them and
Okay.
they get of different complexity and length. But I like that one.
That one, yeah, that was
Right?
great.
I like that one. So I gave that one to Mike to put on the website. But no, I'm not talented enough to come up with anything like that. But yeah, you can, so that shows you, visually mountains rising. It's just rivers. They get above freezing limits in the atmosphere, what we call the snow line altitude of 0-degree isotherm. They get high enough for glaciers to form, and then the glaciers start eroding, doing their thing. And some argue that now. So that's in a general way the buzzsaw is about. Now I'm going to talk more about the buzzsaw, especially towards the end. But I'll mention that a lot of people don't believe in the buzzsaw, believe in quotes, right? Scientists, I like to use the word think. We think, not we believe it. But of course, like anything, you start to get camps and schools of thought and two extremes, two end members. And so there are those who feel strongly about the buzzsaw as being a real limiting issue on mountain height in most areas. And of course, there are those who argue that it's not important. We can ignore those people because they're not in this room right now. But just, I want to make.
We have a Trump problem. Actually.
Well, they had their other arguments. They argue a lot of these surfaces, they're from past river erosion or how things got uplifted. But I'll show some figures during the talk that, of course, are my bias and why I think, I think they're too extreme the other way. Maybe not every single thing is due to a glacial buzzsaw, every mountain peak, but I think it's also too extreme to say, well, the buzzsaw is not important at all. I don't know if anybody would say it's not important, but we're arguing the relative importance in the literature. Here's just some figures of glacier erosion, just to help you think about it on a smaller scale. You recognize this? Central Park. One of those used to be Trump Tower, but it won't be any longer. So I just had to follow up on your joke. This is Bedrock. I think it's near Empire, near 61st Street, Columbus Circle. I've actually never been there. I'm always showing photos of the baseball, Little League areas, but they have some of the best glacial striations, glacial grooves that formed under the Laurentide. Glacial grooves. And I gave it in another workshop. I talked about the area, Empire Rock off Columbus Circle, which I don't think I've ever been to, but this is Empire Rock, I think, off Columbus Circle. This is Patagonia. I spelled it wrong. It should be Torres del Paine. And you can see this is not happening now, but just imagine this big rock is on the bottom of a glacier and glaciers are moving. So they're going to drag these things across the rock underneath them. And that's one of the fundamental ways that glaciers cause glacial grooves, glacial striations, because there's all this stuff sediment and rocks and stuff at the bottom of a glacier or an ice sheet. Since the glacier is moving, ultimately due to gravity, it's dragging stuff across. So that's how the stuff, whether we're looking at Empire Rock in Central Park or this rock in Torres del Paine, which is spelled wrong, it's kind of a similar process. And this happens, happens at a small scale, the size of the table, but these are big landscapes. These are fjords in Patagonia. You think of the fjords of Norway. The Hudson Fjord owes a lot of its origin through the highlands due to glacier erosion. It was like a classic definition of a fjord. It was there before glaciers were there. It's ultimately due to tectonics and where faults are located. But then the ice sheet comes down during the Ice Age and it carves out the Hudson River. It makes it deeper, it makes it wider. And so this is not, you don't think of the Hudson River as a fjord, but people like me think there are parts of the Hudson River, like through the Highlands and the Bear Mountain, West Point area, that resemble a fjord. And it fits the definition of a fjord. These are glacial valleys in Patagonia, big U-shaped valleys similar to Yosemite. This is at 1,000 feet, 4,000 or 5,000 feet, 1,000 meters. So you're not going to get a fjord because it's several thousand feet above sea level. But if this was at sea level, this would be filled with water. This is the Uppsala Glacier in Patagonia. So I don't know how, I can't get rid of that thing at the top, but there's the Andes in the background. This is the glacier. And all this is rock that's really eroded by glaciers. There's my colleague, Jorge Stralin. And this is all, we call this scouring. The glacier, we say it's like a classic landscape of, the definition is aerial scouring. It's a landscape of aerial scouring. And this is what the glacier did to this landscape. Lots of glacier grooves. You can see all these glacier grooves. Glacier grooves tend to be very shallow. They can only be like a couple millimeters or 1/8 of an inch, 1/4 of an inch deep. So they weather away very quickly. So when you walk around this campus and you see rock, it has a smoothness sometimes due to glaciers, but you don't see the grooves around the Lamont campus. They just erode away too fast. The glacier hasn't been here for, depends who you talk to, whether it's me or Dorothy Petit, but at least 16 or 18 or 19 or 20,000 years. Some of the rocks on this campus may have been exposed to the element, and that's more than enough time for any grooves or striations to weather away. So that's why you don't see them everywhere. This landscape was uncovered probably about, it could only be 30, 40 years. Or it could be 100 years, but certainly less than 150 years. So that's why we have these sort of the best examples I can find of glacier erosion, scouring. There's again, Oje for scale. I'm going to see Oje in a few weeks down in Argentina. But you can see this is a landscape really affected by erosion. Some of you have been to the Perito Moreno Glacier. This is near the Perito Moreno Glacier. So just give you a sense of what glacier erosion looks like on a small scale. This is happening over large areas, which gets you to fjords, U-shaped valleys, things like Yosemite. So glacier erosion has a very strong impact on the landscape. So now you can see how it could cause mountains to erode. This is the Andes. That's also the Uppsala Glacier, it's just the same. Yep. The Andes, this is similar to the Matterhorn. This is a glacier, and the glaciers are eroding its side. So you're getting some of these sharp, pointy things like in that video. Glacier erosion. This is Torres del Paine. I didn't spell it wrong on this slide. Has anybody, maybe online, anybody been to Torres del Paine? Yeah. I just had a cousin go there. It's one of the highest tourist spots in Patagonia. But these little pointy things, and there are small glaciers today. Some of them you can't see on this photo, but certainly during the Ice Age, this whole area is really heavily eroded by glaciers. I worked in this area for about 10 years. We had terrible views like this every day. Actually, a lot of days the weather was so bad, I thought, I should have been a lawyer or something. But then you get really nice weather. This is not so nice. You can see the storms coming in, and you think, all right, this is not so bad what I do. Well, I don't make as much money, but. So with, sorry about this thing at the top. I don't even know what it means. Please move this window away from the shared application. So glaciers erode. I just wanted to touch base to mention that in most places on Earth, glaciers, we say they're warm base. That the bottom in places is close to the freezing point, at least in the summer. Sometimes you get a thin film of water because the water is raining down in the glacier. In the summer, it has to go somewhere. And so this causes glaciers to slide on their bed. And this is a really effective mechanism for the erosion at the bed. So this is an area I worked in. Actually, that's me behind the boulder. This is Glacier Frias in Patagonia. All this sediment was eroded out by the glacier. Here's our Matterhorn picture again. There's the picture I showed you of the solid glacier. It just, over the last, I can't remember, a few decades or less than 100 years, uncovered this landscape. Yeah, it's one of the fastest retreating glaciers in South America today. Glacier erosion. This is when the glaciers, this is much of the Andes, although not everywhere. Alaska, you see Alaska has warm summers. Doesn't matter really where you are in Alaska. The summer is going to be warm. You know, warm is relative to us, right? But it's above freezing in most areas in Alaska, especially along the Alaska Peninsula, where the glaciers tend to be. Other areas you could think of where there are glaciers. The Himalaya is mixed. Some areas are, it gets warm in the summer, but for reasons I'll mention, not all of them cause a lot of erosion. Not all of them have a lot of water and erosion. Cirques are these kind of bowl-shaped things you see in the Alps, Norway, Rocky Mountains. Rocky Mountain National Park has some beautiful cirques. Now, that's where previously where the glaciers we say the lingo is they're warm-based glaciers. The bottoms are close to the freezing point, what we call the pressure melting point. We also have places where the glaciers are not, the bottom of the glaciers or the ice sheets are not close to the freezing point. They're actually well below freezing, very cold. This happens almost all, not everywhere, but over much of Antarctica. Antarctica is so cold and that, you know, the bottoms don't get, and it's a large ice sheet, so you're not, parts of it are not exposed. Even if you have places in the atmosphere, places above freezing in the summer, you know, glaciers a few thousand meters thick, it's not going to feel that in the summer. So the glaciers tend to be cold. This is a little glacier in the Transantarctic Mountains. And so it is seeing everywhere in this glacier is seeing the temperature of the atmosphere. It's like a dipstick in the atmosphere. But the atmosphere is cold. This is pretty far south. It was probably about 85 degrees south latitude. It's cold. And it's the coldest place I've ever worked. And which makes sense, it's near the South Pole. Right? But this glacier doesn't erode. It's frozen to the rock. Right? It doesn't, its bottom is not near what I was calling the pressure melting point. It's so cold that this glacier is always just, we say it's frozen to its bed. The lingo is it's cold-based ice. And that's in contrast to Patagonia, the Alps, Alaska, all these other places where I said, you know, glaciers, they're filling a warm summer atmosphere, they're melting in the summer, you're getting some of that water at the bed, and so you get a lot of glacier erosion. The point I'm just making is that it's not everywhere around the world that glaciers erode. There are parts of the world where glaciers don't do much erosion, specifically Antarctica. Now they do some erosion, but just nowhere near the scale of a place like Patagonia or the European Alps. The other thing that's interesting, I had never seen glaciers like this before. It's like the Snuffleupagus trunk. It's like the elephant trunk. They're very narrow. And it's because they don't slide on their bed and that they don't like flow out. You know, you think about when you make a pancake and you pour the batter on the grill, it flows out. A lot of glaciers flow out in that way. You get these Piedmont glaciers. This doesn't do that. It can't move along its base. The only movement it has is due to gravity, and the glacier internally deforms because it's flowing downhill, internal deformation. And that, I found this really interesting. Before this, I never worked in a place where the glaciers are completely frozen to their beds. They don't slide at all. The only movement they have is due to gravity and some ice fall. And that causes these things to be really narrow. It was really interesting. This was in 2011. First time I saw glaciers like this. More Antarctica. It's cold. I can't say. When we flew from 84 to 87 south. And then we camped for about a week, but you know, it's like going into a freezer. I mean, nothing's really happening. I put the chicken in the freezer the other night because I want to eat it for 2 weeks. That's why I think of Antarctica. Now, it was a little different a few million years ago, maybe during the looking at changes during the Pleistocene transition about 3 million years ago. And people like Sid Hemming, who some of you may have met, Sid and her colleagues are studying some changes that may have happened here 3 million, 5 million years ago. It may have been, I wouldn't say it was like Patagonia, but things were a little wetter, a little warmer, things were sliding more. But this is in the last couple million years. So at the top, I say landscapes of glacier erosion. For those who can't see under the red bar, this is kind of the, oh, it disappeared. But you know, just to give you a feel, not everywhere on the planet do glaciers erode, but these are the exceptions, and they're in Antarctica. But the other big exception is, I'm going to skip that for now. This is well, the other place, and I'm going to talk about this at the end, are the places that are extremely dry. And the places that are extremely dry include parts of the Himalaya and parts of the Andes, which I'll talk about. And they're so dry that it's warm enough during the summers for glaciers to melt, but there's not much melting. Any melting that happens in places like the Atacama, Altiplano, parts of the driest parts of the Himalaya, the water evaporates right away, so you don't tend to get much erosion. This is a map somebody put together of erosion and climate, and what it shows is how the erosion has increased over the last couple million years compared to times before that. And so the darker the color means things are eroding faster over the last couple million years compared to the previous few million years. And you see everywhere's pretty dark because the focus is on the mountain belts around the world. So what they were trying to show that in the last few million years, things are eroding much faster than the previous few million years. And they show the areas that are the darkest are Patagonia, the Alps, and the Himalaya. And what this paper was trying to show is that glaciers really do play an important role in how fast things have started to erode over the last couple million years. The key thing about the last 2 million years is called the Quaternary Ice Age. Now, glaciers were in Antarctica. They were probably here in North America well before 2 or 3 million years ago, but the last 2 or 3 million years have been the most intense phase, if you will, of we say the late Cenozoic or the current ice age. The Laurentide ice sheet coming down to New York, covering Lamont, making its way down to Brooklyn. Would it get the congestion charge if it came through? It'd plow right through those cameras, eh? So what this paper was arguing, since the last 2-3 million years have been the most intense phase of the current ice age. Glaciers were around before that, but the Laurentide ice sheet was probably not as big. They weren't coming and going as much. There were more warm periods without ice. They're arguing that this is another sign that glaciers really do matter for how mountains erode, because they're all eroding more quickly in the last couple million years compared to what they were doing before. Now, a lot of people would argue with these kinds of summaries, but it's a pretty convincing figure. Now, in much of the Alps, in the Himalaya, there are no glaciers. I mean, a lot of the Himalaya are covered with glaciers. I mean, you hear about it, it's a really important issue for parts of places like Bhutan, which are heavily dependent on glacier and snowmelt. But once you get to a latitude that's low enough, or lower latitude, the glaciers tend to be smaller or not around because it's too warm in the summer. That snow is not surviving. And so while parts of the Himalaya have large glaciers, parts of the Himalaya don't. And some of these areas have the other main way that mountains erode. Remember, I said the two ways, and the other way being, what do you see on this Google image? Lots of valleys, probably due to rivers, right? River erosions. So places like this are heavily dissected. This is called Nanga, I forgot how to pronounce Nanga. Nanga. Oh, here it is, Nanga Parbat. I'm not pronouncing it correctly, but this area, this paper, it's one of the classic papers in my discipline, geology, showing the effect of bedrock incision, rock uplift, and they call threshold landscape. So they would argue that rivers are keeping a landscape like this also probably in balance between rock uplift, erosion down. As rivers, you think some of these high relief valleys, rivers can become really important. Now, maybe this area had glaciers at one time, eroded them down, but today there might be some small glaciers around the highest peaks, but most of the landscape is just dominated by river erosion. And it's the same thing, once you get in the Andes and you get closer to the equator, you're probably having more and more. You see, you've probably seen these photos of these steep valleys in Peru, Cusco and the famous Inca sites, Machu Picchu, like these steep valleys. These are rivers eroding their valleys. Let me see, I had a break coming up. Maybe about 10 more minutes, and I could use a 5-minute break. So there's a few more things I wanted to just explain, and then maybe we take a short break for 5 minutes. Now, I started introducing this concept of where glaciers tend to do much of their erosion. Now, throughout the last few million years, so this is just kind of repeating or summarizing what I just mentioned. Throughout the last few million years, the current ice age, if you will, glaciers have undergone, they've caused substantial modification of the landscape in some areas, especially in Patagonia, those figures I just showed you, deep valleys, and the temperate mid-latitudes. So I mentioned Antarctica may be an exception. Last few million years, I don't think there's been that much happening in Antarctica. Glaciers are just cold. They're really large. Some of the largest ice sheets on the planet are in Antarctica, but they're not doing as much as erosion as they maybe were in the past. What's happening in Patagonia, the Alps, etc. So for the mid-latitudes, glaciers have had this huge impact on mountain development. This figure on the left was, I deleted the reference by accident, but it's from a paper called Broker and Denton. And in red are the large ice sheets. So here's North America, South America, Antarctica. And in red are large ice sheets during the last ice age. So the Laurentide ice sheet, which covered New York. Much of, this is not quite accurate now, we know, but much of Scandinavia, all Scandinavia was covered. Much of the UK, for the person in Spain, certainly the Pyrenees had large glaciers. Much of Spain obviously didn't have glaciers, but the Pyrenees, the border with France, and certainly here's the Alps. You can see in this figure the Alps, the small ice field of the Alps did seem as big, and here's Patagonia. Now, this is getting back to, this is a glacier, right? And at the higher parts of the glacier is where the snow falls. We call that the accumulation area, because that's where snow is accumulating. And then below that, where you tend to get more melting at lower elevation, we call it the ablation area. It's where the ice is and the snow is ablating. The boundary between those two things is called the equilibrium line altitude. The equilibrium line altitude is where at the end of the summer, the amount of snowfall over the year is in balance with the amount of melting in the summer. In some places, you could have melting in other seasons, right? The spring and fall. So this term, ELA, equilibrium line altitude, is a really important term in a lot of disciplines. Glaciology, geomorphology. You'll see in a few minutes why I'm spending so much time on it. Again, the ELA is where the balance for a glacier is through the year between how much melting is occurring down low and how much stuff is. Now, a lot of glaciers, what's happening with global warming is this ELA is rising. And so for some summers, for some glaciers, like in the European Alps, this ELA is no longer somewhere along the glacier, it's near the top. So that means most of the glacier is melting. In other areas, for a few years, the ELA could be closer to the bottom. But if you see if the ELA moves down because the climate gets cold, the whole glaciers in the accumulation zone is going to keep growing, like during the Little Ice Age. Conversely, if the ELA is near the top, like a lot of areas right now, the whole area is in a net zone of ablation. Even if it snows in the winter, which of course it snows in the winter in the Alps still, there's so much melting through the spring, fall, and summer that the net or average ELA over the year is going to be too high and the glacier is going to be shrinking. So this, just keep in mind this term ELA over the next few slides. The other important thing for glacier erosion is the ELA tends to be the spot of one of the thickest parts of the glacier. It has to do, that's a little more complex to get into, but it has to do with this, all this ice flowing together. It can have the deepest part underneath the glacier. So the ELA tends to be the thickest part of the glacier. And that is a place where much of the highest erosion rates occur. A lot of erosion, if you remember, I said happens up high, but also a lot of erosion can happen around the ELA.
Could you repeat what ELA stands for again?
Yeah, I should have spelled that out. Equilibrium line altitude.
Okay.
I actually have two slides, and the other slide is spelled out. I must have swapped equilibrium line altitude. I could spell it out. Sorry for the folks on TV. I'll mention it to you. I could. Equilibrium line altitude is a really important term. If you type it in, you can read about it on Google, Wikipedia. So much stuff will come up. I think it was even used on that video. Now, here's the reference, Broker and Denton. So what Broker and Denton did, and this will be important for the next couple soon. So here in red are where the glaciers were. That's just to help us remember where the ELA is, where the glacier is. And they put together this figure. So this is from the South Pole to the North Pole. Sorry, I guess folks on TV can't quite see me, but you can see the screen. The North Pole being at the top, the South Pole being at the bottom. What it's showing is, and this is a figure somebody named Steve Porter put together, is it's got a topographic profile. So it's got the heights of the mountains, the highest points. So going from basically the South Pole, but let's just think the southern tip of South America to Alaska. You're looking at a profile of mountains. Right? You're looking at the mountains. So it's like a topographic profile from the tip of South America to the tip of Alaska. The next thing I want to point out is this red line, which is this ELA, equilibrium line altitude. It's showing kind of the midpoint of where the glaciers are. Now look at the red line, how it tracks the tops of the mountains, right? The other thing on here to look at is the blue or green-blue line to the left, and that's the ELA or the equilibrium line altitude during the Ice Age. It varies from place to place, but in general, it's about 800 meters to 1,000 meters lower, 2,000 to 3,000 feet lower during an Ice Age. But the key thing I want you to appreciate here is look at the mountains and look at the red and blue lines. You don't see the mountains going much to the right of the mountains. This is where the glaciers are. The blue is during the Ice Age. The red is now. Now there's a couple places, and this is really important, and it's the focus of the project I'm working on now, where a lot of these peaks do go to the right of the red line. And one of them is in the central Andes. It's kind of like 20 degrees south. Patagonia, I guess you can't see it in the room, but actually this big blob to the right is actually the ice field. It's not a mountain. It's actually, this is a profile of just the highest spots. And so once you get into Patagonia, they're measuring the top of the ice fields. I had another figure that's a little better. For those online, you could probably see my cursor. I'm pointing to this thing. This thing is an exception. It's to the right. Oh, you can see it in the audience. This is to the right of the red line, but this is the glacier. This is the ice field. Right? But if you look at the mountains, for most of the red line, there's nothing to the right. I mean, you get these little bits, highest points. This one part of the Andes is an exception, but it's just, these are just the highest peaks getting. But if you look at the picture overall, you're seeing there's not much to the right of the red line. And some argue this is the buzzsaw. This is going back to the buzzsaw. The glaciers, they erode where they grow, and they create a balance. They keep things in balance. There's rock uplift, glacier and rivers take it down, and if the mountains are not rising too fast. Now, of course, getting back to your question, the rate can vary. Some places can rise a lot faster than other places. So you could imagine if you have one mountain massif rising very fast, it could outpace any erosion taking it down. But overall, when looking at figures like this, many people use these kinds of figures to argue that glaciers and rivers and the erosion they do is keeping it in balance how fast things go up. Because you're not seeing a lot of landscape to the right of the red line. And even the blue line, which is the Ice Age ELA. Now, this was put together by Broker and Denton. It was based on another work by somebody named Steve Porter. He was a professor in the University of Washington, Seattle. And many people have, this is 1989. Steve Porter had actually put this in one of his, he used to write a lot of intro to geology textbooks called then he started writing, they were called the Blue Marble. And he put this together for one of his textbooks. Since then, many people have come up with similar figures on the right. They've done much more sophisticated analysis. They've had their PhD students doing, 3-4 years of the latest digital elevation model and ArcGIS and fancy schmancy way of doing this. They come up with something similar. They may show more detail in certain areas, but it's basically showing the same thing. There's not much happening above where glaciers grow. There are some exceptions, like Antarctica, but I mentioned Antarctica is an exception because the glaciers can't really erode, except in a few places. This is Patagonia, this is the glacier in Patagonia, and these are the Central Andes, which I'll discuss after the break. I'll discuss why some of these areas might be poking through the red line. Here's another way of looking at this figure. This is latitude. It's basically just the southern hemisphere. So we're focusing on, here's where the ice field is more clear. This is focusing just on the Andes of South America. Just everyone can see when I use my pointer. That's the northern Andes. Look, there's hardly anything coming through the red line. Again, the red line is the modern, at least prior to about 2000, equilibrium line altitude. The blue line is the LGM. Some people call it the snow line. It's where snow survives the summer. It's kind of the same thing. When we get to the central dry Andes, which I'll talk about after the break, a lot of these highest points are poking through, and I'll explain why. And then here's the Patagonian ice fields, which they poke through the red line, but that's the glacier itself. If you look at the landscape of Patagonia, remember those aerial scouring photos I showed you? Deep fjords, deep U-shaped valleys like Yosemite or parts of the Alps, including what's the name? Zermatt? When you take the train up, you're going up one of these valleys.
I know, spent them.
Yeah. You could look at the gray, which is the bedrock underneath the glacier, right? Nothing's really poking through the bed line. This is generalized. There might be some peaks that get through, but nothing's poking through, right? So that's another way to see these things called the snow lines or the equilibrium line altitude or the freezing point. These are all the same thing. Another figure where people would say glaciers and rivers, they're keeping things in balance, right, between rising up and going down. People have done extensive studies about this. This is a paper from somebody named Dave Montgomery in geology. The title, Climate, Tectonics, and the Morphology of the Andes. And I'll just focus on the left figure. This might be this left figure, the gray, sorry, no. The red circles are the modern ELA, the blue circles are the snow line during the Ice Age. So they show the maximum elevations, which are this line, and the mean elevations, right? That's another way of looking at it. the mean elevations always seem to be lower than the glaciers, although I don't, that's debatable how that is important, but look at the maximum elevations, which is the thin line all the way to the left. In Patagonia, well, I guess they were pointing out the mean elevation, but look how much lower the maximum elevations are in Patagonia. So some things are getting above the ELA. But look at this breaker on 3540 south where the mean elevation, the maximum elevation of the Andes goes way down. And this paper argued that the reason Patagonia has lower elevations, the gray line, is because of glaciers. It's because these blue and red circles are cutting it down. Once we get up to the central Andes where the glaciers were smaller, things tend to be higher. And they did a bunch of ways to look at this. And in a nutshell, they said this break in elevation, people have flown from Santiago down to southern Patagonia. You really see this from the plane. All of a sudden, the Andes just drop in elevation. You get the volcanoes. Aconcagua is one of the highest mountains in the world, 20,000 feet. And then at around 3540, you can just see this drop. Now, there are others that argue this is too simplified. It has a lot to do with plate tectonics and how the continents are colliding. And I think they're true. I think it's not an either or thing. I think both things are playing role. I think the tectonics changes, rock uplifts, but the glaciers in Patagonia are also causing these things on the left to go down. Oh, let's skip that. So I thought now maybe take a 5-minute break because I'm running over. I don't think the second half will be as long as the first. It's a 5-minute break. If people want to use the restroom. This is I mentioned I was going to introduce a paper and a study that's arguing that climate itself can cause. I've been talking in a way that the mountains go up, rock uplifts, then they come down due to erosion, glaciers, rivers, other things like landslides and rock falls. There's a study in 1990, it's considered one of the most important studies in the field that said, well, it's a chicken or egg issue. And the title, Late Cenozoic, which is the last 50, 60 million years, uplift of mountains. Is it a chicken or egg thing? And what their thesis was that what happens is erosion takes away stuff, and then the mountains bounce up because you remove, it's called the isostatic effect. You take away the overburden. You're covering something with a lot of rock, it's really heavy, or ice. Take that away, things are going to go rise because they're no longer under this thick mass of rock or glacier. And it's called isostasy, isostatic rebound. And it happens on a different scale here under the Laurentide ice sheet. The Laurentide ice sheet, so thick, it's so heavy, it actually pushes the landscape down. And when it disappeared, parts of the Arctic and even Maine, I did my master's thesis mapping these limits around Maine. Oh, my master's degree. I pushed the landscape down a few hundred feet, or 200-300 feet. The weight of the ice sheet. So you take away the ice sheet, it bounces back up. That's called isostatic, glacial isostatic rebound. This is a case where we're not talking about glacial isostatic rebound, although that could be part of the mix. They're just talking about isostatic rebound. So basically what they're saying is you take away this massive rock, it's really heavy, land's going to bounce up a bit. It's just like sitting on something. Well, and then, and they argued that it's a chicken or egg thing. Maybe the cooling, so late Cenozoic led to the current ice age of the last few million years. Remember I mentioned the last couple million years have been the most intense phase of the current ice age. It actually started a little earlier. Antarctica probably had permanent ice around 15 million years ago. 10 to 15 million years ago, Antarctica started to have permanent ice. Greenland had large glaciers. And then in the last 3 million years, it was the most intense phase where we're getting the Laurentide ice sheet coming down to Brooklyn, Staten Island. Parts of Antarctica didn't change that much because most of Antarctica much of it's covered already. What limits Antarctica is the sea. It gets out to the sea and it really can't go any farther because it starts breaking apart and calving. So parts of Antarctica can grow a little bit, it can get a little thicker, but Antarctica can't really grow much Because what's limiting Antarctica now is the fact that it's in contact with the ocean and that causes icebergs and breakups. Antarctica is interesting, though, doesn't actually change. It changes a little bit during ice ages, but the biggest changes are here, right over North America. Much of North America is covered by a giant ice sheet, much of Scandinavia, much of the Alps. And this really got going in the Northern Hemisphere in the last 3 million years. And this is a bottom plot of age. So sorry, folks online can see it. 60 million years, 40 million years present. And what they're showing is elevation of the Himalaya. And they're arguing the fastest parts of the Himalaya, the most elevation increases have been in the last 5 or 10 million years. And that's the same time as the current ice age, the most intense phase of the late Cenozoic ice age. So Peter Monar and Philip England, Peter was a PhD student here in the 60s and 70s. He just passed away a few years ago. Occasionally he'd reappear. You ever see Peter? He was at workshops or events. They argued that it's a chicken or egg thing, because what happens is this cold phase of the ice age over the last few million years led to big glaciers. These glaciers cause glacial erosion. Glaciers are one of the most erosive things we have in geomorphology. The glaciers eroding away the mountain led to isostatic rebound because you're taking away all this rock mass. So they said it's a chicken or egg thing. They argue some of the highest, it's not that the uplift comes first and then the erosion is a response. The climate causes the erosion, and the erosion itself can cause the mountains to go up. So I mentioned this at the beginning of the talk. I was going to come into an example that shows that these lines are starting to go every which way on that flow diagram like this. It's not mountains rise, erosion down. They're arguing erosion itself. Once you get mountains high enough to that video and you start getting glaciers, but this also could happen with rivers, and you start removing that rock mass due to erosion, that in itself could cause mountains to rise due to the isostatic rebound. So they say it's a chicken or egg thing. The jury is still out. So there's been some articles that really don't like this, and they're arguing this is just not applicable, it doesn't happen. What they argue is glaciers cause the erosion. Places like the Himalayas, just in these narrow valleys. Think of the U-shaped valleys of Yosemite, the ones I showed in Patagonia. You know, they're kind of the Hudson Fjord, these kind of narrow spots. They argue that's not, they tend to be confined in the valleys. It's not big enough to cause like something like the Himalaya, which covers a large part of the continent. That's maybe another end member school of thought. There's a lot of these things that might lie in the middle, right? In some areas, this may be a true issue. It's a chicken or egg issue. Other areas, maybe they're right. So, you know, I assume people had thought about this before 1990, but this really said the kind of recast thinking about mountain uplift, worldwide cooling during the last few million years has led to this chicken or egg problem. You right, Mike? Did mountain growth? I mean, you had to have rock uplift initially without erosion, but once erosion really kicks in, especially glaciers, it could erode stuff, and then that could lead to the chicken or egg thing. Again, to emphasize, this is not accepted by all. I could find some articles that are, you know, vehemently opposed to this idea that it's not happening. Jury's still out. This is an example of, in the paper, high landscape. You start to get glaciers and rivers causing deep incision, and that leads to the peaks rising. So, you know, that kind of ties together some of the things. Think back to that flow chart I showed at the beginning. So the research I started off the talk by saying, I'm working now in the Central Andes. I'm looking at the buzzsaw and the effect of glaciers in the Central Andes. That ultimately led me to think about giving this specific topic today. So I just thought the rest of the talk is really just on two applications, two ways that I'm studying these issues I just spent the last hour and 15 minutes talking about. So hopefully that laid some of the basic stuff that we think about that could be happening. Now the rest is really focused on two different research projects I have with colleagues studying all the topics I just spent 75 minutes talking about. The first is in South America, in the Central Andes. It's the widest and highest. Well, in average elevation, it doesn't have the highest mountains, but it has on average, the highest part of the Andes. And Costa Rica. Now, Costa Rica, I worked there with a student, Max Cunningham. He was a PhD student here at Columbia University. He came to me it was about 12 years ago. He goes, I want to study glaciers in Costa Rica. And I said, Costa Rica? There are glaciers in Costa Rica? It's in the tropics. Now, I grew up in the Bronx. I think of Costa Rica, I don't think glaciers. But during the Ice Age, there was a small system around the highest peak of the Talamanca. So Max's PhD was to focus on the buzzsaw, where the glaciers have an effect in a place like Costa Rica, which is in the tropics. This project is in the Andes, Central Andes, at around Tropic of Capricorn, 23, 25 south. And this is the driest part of the Andes. It's very dry for a couple of reasons. One is it's under the subtropical highs. It's like the Sahara. It's just a naturally dry part of the planet. And it's also got a big orographic rain shadow. On the east side is the Amazon basin. The rain's coming in from the Atlantic. It just can't make it over the mountains. And this is the subtropical high, like the Sahara, where it tends to be naturally dry anyway. So it leads to the Atacama Desert, some of the driest places on Earth outside of Antarctica. So our ideas, we wrote this proposal I mentioned 4 years ago today, in April. I was working on this proposal during the lockdown. And we thought, well, maybe this is a good place to test the buzzsaw idea. Because it's still like a lot of things, nothing is answered definitively yet. And research, often at the end of your project, you got more questions than you started out with. That's how science works, scientific research. Let's go to an area where we can remove, remember I said rivers, glaciers, precipitation, glaciers. Let's go to an area where we could kind of remove one of these so we could try to isolate the study of glaciers. So we thought by going to this part of the Andes, it's one of the driest parts of the planet outside of Antarctica. We can maybe more focus on the glacial process because we're not, the rivers and rain and not causing as much change. So we thought when we wrote the grant. So the first, we went to the Central Andes. That's me. Mateo, my colleague, in 2 days dragged me up from 1,800 meters to 3,000 meters in a 3-day hike. I lost like 15 pounds. That's me. I don't look too tired after being dragged up 3,000 meters in 3 days. But look at the top, glacier erosion, right? This is the highest peak. This is called Nevado de Shani. It's about 6,000 meters, actually, 18,000 feet. But look at the top. It looks like the Alps. Looks like parts of Patagonia because the glaciers are eroding up here. And then once you get below the equilibrium line altitude I wrote on the board, or snow line, you're not looking at a glacial landscape. It's an old Inca trail that actually went over the mountain. So we went up there. And this is the area on the left on Google Earth. Zooming in is on the right. So here's the field area I showed. And I just want you to appreciate the difference on the east side or the right side of the figure versus the left side. Let me do this for the people. So on the right side of this figure versus the left side, both sides are glaciers, have glaciers during an ice age. They don't today. It's too warm and too dry. But on the right side, look how much bigger the valleys are, the yellow line versus the red lines. So the left side also has glaciers. Think of that. Remember that photo I showed of the glacier in Antarctica? It's very narrow. I think the left side has these kinds of glaciers. Very narrow. They don't do much erosion. The right side, which is the side facing the Atlantic Ocean, gets a lot more precipitation. It gets a lot more snow, a lot more rain. We've been there in days when you see the clouds coming up. The right side has a lot more precipitation. The glaciers were bigger. The left side, the glaciers are smaller. But we put this in the proposal saying we want to study the east side versus west side. Clearly, just looking at this simple Google Earth image, we could do in 30 seconds. You could see the impact glaciers have had on this side, but not on this side. So we're using a bunch of techniques to try to figure out over the last few million years, or even the last few 100,000 years, how much do glaciers actually erode the east side versus west side. Now, the reason on the left side, these glaciers may have been smaller where it's drier is because I did mention this, similar to Antarctica, the glaciers, when it gets really, really dry, they don't do much erosion either. So that's the other part of the Earth where it might be warm enough for them to slide or to move, but it's so dry that when they melt, it quickly gets evaporated. So you're not getting a lot of water getting to the bed like you do in Patagonia or the European Alps. And so these glaciers, this is the other place where I think I'm looking at glaciers. They're these like narrow elephant-like snouts. They're not like typical glaciers I see where they kind of flow out. And I think that's because they're not frozen to the bed. If you remember, I used this term cold-based ice for Antarctica. It's so cold that they're actually frozen to the rock, so they're not doing that much erosion. In this case, they're not frozen to the bed. They're just not moving much because it's so dry, there's no water, and they're not sliding. For glaciers to really slide, it helps to have a lot of, even it's very thin, water at the base. So we're looking at all these different things. On the right side, this is the highest peak, Nevado de Shani, where you can see there's some glacier erosion. And we're studying in red, these red outlines are these different catchments, river catchments. We're literally going from the highest catchment all the way to the left side, which is some of the lower catchments where there are no glaciers. There probably never been glaciers. And so we're looking at different methods to look at, different methods to look at how fast these basins are eroding out and seeing if as we go, in this case, from right to left, does the amount of erosion become less and less over the last million years or a few million years? So that's the way we're trying to address this study. We argued in the proposal, it's like a natural laboratory experiment. We had a catchment, a river catchment that's glaciated up high. We can go to the left. This is 10 kilometers. We can sample these areas, and then we could compare how fast these things are eroding. The bottom figure is just like they're like mug shots. No glaciers, areas that have some glaciers, but not so much. And then on the right is Nevado de Shani, which is heavily glaciated. So when I'm going in about a month from now, we had a big field season last year. All of these catchments on the right side we got to, but some of these, ironically, actually, some of these ones are the most remote from roads. And we couldn't figure out at the time an easy way to get there. And so we're gonna go back there at the end of April, end of tomorrow's month. Monday's April. And so in 4 weeks, we're gonna focus on the left side. So that's one study we're doing. And we have a couple of hypotheses questions we're addressing in this study. One is part of the research is just to improve how climate has changed in the past. Because remember those flow charts, climate is still there as one of the biggest boxes. It causes the glaciers to grow. In this case, what the climate may do during an ice age, it may become wetter. We think it's not as dry during an ice age. That's why you get glaciers growing. So we want to find when times were wetter. So we're using a bunch of techniques to do that. And that's one of the big objectives of the project is you remember the boxes. Climate is one of those biggest boxes. So we also have to learn about that. And so we're using a bunch of techniques to do that. We're mainly reconstructing at what time the glaciers were around. The second one you see to improve understanding of the processes that have shaped the arid Andes. And I just mentioned we're going from catchments that are heavily glaciated to ones that are lower, haven't seen glaciers anytime soon, at least recent. And we're looking at how glaciers have impacted the landscape directly. Remember the one figure I showed? The right side of the figure, you can see the deep valley versus the left side, which had glaciers. They just weren't eroding because it's drier. And then indirectly by maybe affecting river networks because they melt and they cause a lot of river erosion. And the question is, does this limit mountain height? That's our big question. We may not answer this question at the end of the project, but this is the overarching question. That's what on the left is the west side, which is the really dry side. This is the shrubs The right side is wetter. It's kind of relative. It's not like the Amazon. But you get monsoon rains in the summer. It gets pretty wet. I've been there during rainy days. I was gonna go through this, some of the data. What we're seeing, we've got some data. What we're seeing is the raw precipitation and where it rains is more important than we thought. We thought it was just, the whole area was just so generally dry that it didn't matter. But what we're discovering is, it's hard to see here because of the. There we go. Maybe you can see better. You can see that the right side is green. The right side of the figure is more green. That's the Amazon. Well, not the Amazon. It's the moisture coming in from the Atlantic. Get the orographic effect. The left side is dry. And well, we're finding this is in meters per million years how fast things are eroding. This is 25 meters per million years. These are the glaciated catchments. The star is the highest point. Down here, it's, I know in the audience you can't see, but it's around 300 meters per million years. That's how fast things are eroding, probably in the last 100 or 200,000 years. So these things are much higher. They're higher actually than where the glaciers were. But the samples we collected and the catchments are, it's hard to see here, but they're closer to the green. So it probably doesn't take much precipitation to really matter. We're now trying to do transects in some of the glaciated areas to try to narrow down the effect.
Mike, in the upper right corner. What's moving the rock
This
pieces?
What's that?
What's moving those rocks? Is it?
Well, now it's a dry riverbed, but when the monsoons come in the summer, the water is probably 10 feet high. Yeah, it's a real monsoon spot. So yeah, it's like any monsoon area, this is most of the year, this is a dry riverbed, and then for a couple, 2-3 months of the year, during when the E2C shifts to this part of the planet in the Tropic of Capricorn, this river is several feet high. So there are no glaciers today, it's all river. It's only during the ice ages where the glacier erosion happens. Anyway. Have people heard the term thermochronology? It's basically, as the landscape rises, this is the temperature. As you go down in the crust, it gets hotter and hotter, right? And that changes minerals as things the other way. As you come up in the crust and things get cooler, minerals change, if you will. And certain minerals, they leak certain elements until they get to a certain temperature. And once they get cold enough, they kind of lock in their chemistry, if you will. And we have a bunch of tools to see that. We can see when minerals cool to a certain point. Like when minerals are too hot, but as the rock comes up, either due to rock uplift or isostatic rebound, that rock is cooling. Chemistry is changing of the minerals. At some point, things become cool enough that the mineral kind of locks in its chemistry, if you will. And the techniques you use to see that when things lock in is called thermochronology. Thermal being temperature, chronology being chronology of the temperature. Right? And the bottom figure is another, shows different temperatures as you go down or as you come up, depending on which way you're moving. And so we're also using this technique called thermochronometry. We're seeing how long ago the rock uplift brought the minerals to a certain temperature as it's rising. And we're getting about 10 million years. These three numbers are all 10 million years. We're using a bunch of techniques, but this is one of them. So that's saying that this rock came to the surface or it came close to the surface in the last 10 million years. What's 10 million years? It's the late Cenozoic Ice Age. It's going back a little earlier than that. The one thing I should mention, the Laurentide ice sheet's been coming down here for about 3 million years. The Andes probably started having ice between 5 and 7 million years ago. Even most of Canada was probably heavily glaciated 5 or 7 million years ago. But the Andes probably it's 5 or 7 million years that have much of the Patagonian ice sheet has been. So it's getting close to that. We're not seeing that. If we go to other areas, data that other people have gotten, we see 50 million, 100 million. So we think, just to give you one take home of the first sets of analyses, we're getting 10 million years that the rock has kind of come up near the surface So we're probably gonna, I think this has to do with, it's either the cooling over the last 5 or 10 million years, what's due to the effect of glaciers. I'm gonna have to skip that, but the second area is the tropics. Remember I said Max dragged me down to the tropics? This is Costa Rica. It's a Talamanca range of Costa Rica. And the maximum peak is around 4,000 meters. I'll talk about why that's important in a minute. But that's the Atlantic Ocean, the Talamanca range. This is the highest part of, most of the volcanoes are off to the left. They're not in this area. And this is zooming in on Cerro Chirripó, which is the highest point of Costa Rica, highest point of the Talamanca range. And what do we see on the Google Earth image? Rivers or glaciers, showing you some of those landscapes I showed.
I was just in Costa Rica a couple of months ago, and there's one area where it has a U-shaped valley, and cruise ships have a problem when they go past that. The winds are constantly between 35 and 50 knots, and the seas run 17 to 25 feet. We had whitecaps breaking on deck 6 against the windows. And that's the only U-shaped valley we passed where they have this problem. And it never dawned on me that it could have been glaciated, that valley, because everything was a V-shape.
Now, if it's near the sea, probably. This is
Oh,
just
yeah.
the highest point. No, I think near the sea. No, this is just the highest points.
They actually have a logo that they post when you go through that area.
Yeah. I think what we're finding is, in that case, that U-shaped valley, maybe coincidence, it looks like a U-shaped valley because the glaciers didn't make it down to
one, and the winds are awful, and the
Yeah.
seas are terrible.
the glaciers didn't make it down to sea level. They basically just covered this area, the bare rock area. So it's just the highest spots. In the tropics, during the ice age, there were glaciers. In some areas, there are still glaciers today. Mount Kilimanjaro, right? The snows of Mount Kilimanjaro. Until recently, they had small glaciers. Cerro Chirripó and the Talamanca range, the glaciers were just confined to the uppermost. It must be just coincidence, some other bunch of processes by coincidence. But this area, this is the highest point, zooming in. We see a U-shaped valley. Here's a set of glacial moraines. It's not for you to see perhaps, but coming down, if you see this line, that's a moraine. Just like in Rocky Mountain National Park, on Long Island, Staten Island, it's the same kind of landform as in Staten Island, Rocky Mountain National Park. It's a glacial moraine that's coming down right here, going up the other side. So this is I wouldn't call it a U-shaped valley, but it's a wide, deep valley due to glacial erosion. It's harder to see on here, but the highest point is surrounded by little cirques. There are a bunch of 3 or 4 cirques, those bowl-shaped features that you get small glaciers in. Very nice landscape. And we get down, we see glacial striations. I think I took those pictures out. Yeah, I took those pictures. Yeah, we get glacial striations, etc. The highest parts are glaciated. And we're working on when the glaciers were there and the effect they had on the landscape. So this is an example of, here's a cirque. And then a river. Max's PhD, or part of the work he did, was mapping which areas were really affected by glacial erosion, and blue, which areas were really affected by rivers. So the glacier only came down to here, didn't go that far down. And then you get the steep drop off and you're dealing with rivers. That's me. Another part was a graduate student much younger dragged me up to 14,000 feet in one day. I lost about 10 pounds. That was an Antarctic period, actually. That was a guide we had, his interesting story. He had come, now he was in his 40s. That time they were similar age. And when he was 18 and 20, he came to the US illegally twice. And as we're up there camping, he's just telling us these stories of coming across the border with the coyotes. This was 30 years ago. It's like really, we're like, oh, it's very intense, these stories. I think he did this in the 80s and 90s. That's Max in the middle. So what Max did is that's just Costa Rica, which is the second area we've been working in. What Max did is in this paper, he looked at all these little things are all different mountain ranges around the world. The upper left one is Indonesia. Taiwan, this is Costa Rica, which I just showed you. Borneo, Papua New Guinea, Venezuela, Colombia, and East Africa. 10 different mountain ranges all around the world. And he concluded that they don't get any higher than a certain point for a reason. They all seem to max out around 3,500 to 4,000 meters. Here's Chirapa, 3,900. None of these areas are getting above 4,000 meters, 14,000 feet. All 10 areas. So he wrote this paper, Glacial Limitation of Tropical Mountain Height. Even in the tropics, the warmest part of the planet, he thought he could isolate this effect of what I started off the talk by calling the buzzsaw. Right? He argued in this paper that it's too much coincidence that you look at 10 different mountain ranges around the planet, Southeast Asia, Africa, South America, Central America. All these places don't seem to be getting higher than 4,000 meters. What do they have in common? Glaciers above 3,500. During ice ages, they have glaciers. So Max, in this paper, the main thesis was, now, of course, people are going to debate with us and argue there are other things that could cause that, but that's actually our hypothesis. That's our opinion that what are these 10 mountain ranges on how many continents? Africa, Asia, Central America. Well, Central America is not a continent, but South America. Let's say 4 different parts of the planet. The one thing they have in common that their mountains are not getting above 4,000 meters is they have large glaciers. So in this was the second thing. We're still kind of working on this. You know, if we just go back, I'll just go way back to the snow line figure. Excuse me. This only goes to 10 degrees, but remember this figure I showed you was going from the tip of South America to the tip of Alaska or North America. The red line being where the glaciers are now, the modern equilibrium line altitude. This is the tropics here. You don't get any high mountains. Now, I think people who are focused more experts on tectonics and mountains, how they rise, might argue that right now, maybe coincidentally, there's nowhere in the tropics that could lead to high mountains, the plate tectonic setting. But in our paper, our opinion is that that might be playing a role, but places like Papua New Guinea could certainly get high enough. Venezuela could get high enough, but what's keeping this dashed line not getting to the right of the red line is simply the buzzsaw. Not simply, but the buzzsaw. So anyway, that was all I had to say. Well, I had to say a lot more, but I've said enough. There's other things I could talk about. That was. Oh, there's another version of that, but that was the end of my talk. So.
Thank you very much.
Very good.
So sorry, I went on a little bit long, perhaps, but it's just totally an hour and 45 minutes. So those are the 2 studies we're trying to get at this problem. The Central Andes and working in the tropics.
Good luck to you with the field research.
Yeah, we're leaving in 3 weeks for the tropics. I mean for the Central Andes. Actually, I'm teaching a short course. First, I'm going to teach a short course in Cordoba, similar to today's class.
Thank you.
Excellent. Thank you very much.
Thank you. Yeah.
Okay. Chris, you stopping the recording?